In this video, we present SOMA, from surface observations to muscle anatomy. State-of-the-art virtual human models capture the skin, but they remain hollow inside. To truly virtualize ourselves, we need the whole picture: bones and muscles. Real human motion involves muscle bulging, skin sliding, and volume compression, dynamic effects that standard skinning simply cannot reproduce. Traditional physics-based simulations, like FEM, are highly accurate but computationally expensive and hard to scale. We are stuck choosing between the efficiency of basic skinning and the high cost of physics. We need a middle ground. Our goal is to learn skeletal motion-dependent muscle deformations solely from multi-view videos rather than relying on expensive and hard-to-acquire CT or MRI scans. To solve this, we present SOMA, a subject-specific model that recovers complex muscle anatomy directly from surface observations. At test time, our method requires solely the input motion and the anatomical canonical templates for the subject to reproduce accurate muscle and skin predictions. To power this, we introduce SCIM, a high-fidelity dataset that bridges the gap between outer surface tracking and internal anatomy. We start with volumetric scans to build precise, subject-specific anatomical templates. Using a custom RUCO-embedded suit, we generate a dense canonical point cloud that maps the outer skin to the internal muscles. Captured through a multi-view camera setup, this allows us to track dense, temporally consistent surface deformations across highly dynamic motions. We capture dense surface correspondences across space and time, achieving a spatial resolution, intermarker distance, of approximately 1.5 cm. We use this rich surface data to correct standard skinning errors, extracting the exact 3D displacements needed to drive our anatomical model in canonical space. To our knowledge, we are the first to utilize vision data to accurately reconstruct person-specific internal muscle motion over time. Recent work, like HIT, attempted to infer internal anatomy from outer skin surfaces. However, as a volumetric fitting approach designed for static shapes, it lacks dynamic consistency. Furthermore, because it relies on generic body templates to guess the inside from the outside, it struggles to adapt to individual human proportions, often leading to severe anatomical collisions and high tracking errors during movement. SOMA flips this paradigm. Instead of guessing from the outside in, we build a subject-specific model driven from the inside out. We start with a personalized anatomical template. By linking the skeletal pose directly to our internal muscle layer, we provide the network with explicit mechanical drivers. Using the high-fidelity surface tracking from our SCIM dataset, SOMA learns decoupled, pose-driven blend shapes. This allows the network to predict exactly how individual muscles will bulge, stretch, and slide during any given movement. But data alone isn't enough to guarantee biological accuracy due to the ill-posed nature of the problem. Using our physics-based geometric priors, we can enforce volume preservation and biomechanical membrane tension during training. Here are some final results. The skin, muscle layer, and individual muscles are shown in the left, center, and right, respectively. A heat map measures the surface change with respect to the rest pose, describing positive and negative deformations due to the input motion, for instance, for these different exercises that involve heavy lifting. Here we show more results, for example, predicting physical changes in another subject. Or showing the prediction in movements out of the distribution. Thank you.